Chapter 8 is the first chapter for Chem 102. So I'm going to first introduce you about the learning objectives of the course of Chapter 8. Uh, we're going to discuss about different types of chemical bonding. Really, some of the things are it's extrapolation of what we discussed from Chem 101, even though I'm not expecting that everybody took Chem 101 just last semester. So for some of you or many of you, it might be a new term or you took chemistry a long time ago. So if anything is not clear, like I say, raise your hand and then I'll try to explain it to you. Chemical bonding was discussed in 101, but we're going to expand the idea of chemical bonding in this chapter. We're going to discuss about quantitatively how do we describe the energetic factors involved in the formation of ionic bond. We also discussed about how we calculate lattice energy, the relationship between lattice energy and the physical properties. Let me go back here. Also, we're going to discuss about the Lewis structure, electron dot symbols to predict the number of bonds of an element will be discussed. If we have time left, I'm going to also provide you some examples. We're going to discuss about examples. How do we do Lewis structures? What are the main? How do we explain distributions of electrons around the molecules? That's one of the things that we're going to discuss in this chapter. We also discuss about the concept of resonance. How do we assign a Lewis dot symbol to elements that do not have an octet of electrons in their compounds? Identify the Lewis acids and bases will also be a part of this chapter and go today. Okay. So first, I would like to start with the overview of chemical bonding. Everybody knows that there are two different types of bond. The common bonds that we discuss when we're discussing about chemical bonding is ionic bond and covalent bond, right? Okay. I'm just writing a common definition of bonding, ionic bond versus covalent bond. Um, a covalent bond this is working here. When I say BN, it's I mean that the bond between okay, let me see, non-metals. Okay, so I'm just writing the definition of bonding. The common one are ionic bond and covalent bond. Ionic bond is a bond of ionic bond mostly formed between metals and non-metals. A covalent bond is a bond between non-metals and non-metals. Having said that, for example, if we have a bond of attraction between common one would be sodium and chlorine, would be sodium chloride. This can be a good ionic bond. We have also like a bond between two nonmetals. Let's say nitrogen reacts with oxygen. It can be formed nitrogen dioxide, something like this, considered as a covalent bond. This is a bond between nonmetals, and nonmetals will be considered as a covalent bond. A bond between metals and nonmetals will be considered as ionic bond. This is what we discussed from our Chem 101 or other areas. Here also, there is an extrapolation of the bond. A chemical bond is the force that holds atoms together in a chemical compound, the force of attraction that brings atoms together, excuse me, that brings atoms together in a chemical compound is considered as a chemical bond. So we have covalent bonding, which means that the electrons are shared between atoms in a molecule, or a polyatomic ion. Most of you are familiar with the polyatomic ion. It's a group of ion, a group of atoms that have an overall charges. So the common polyatomic ions, if we have like SO4 minus 2, for example, is a polyatomic ion. Sulfur and oxygen has overall charge of minus 2, is a polyatomic ion. It's the bond between sulfur atom and oxygen atom is a covalent bond. We have nitrate ion, for example, NO3 minus 1. It's a bond between nitrogen and oxygen, is also a covalent bond. Um, what's the fundamental point here? In ionic bond, the positively and negatively charged ions are held together by something called electrostatic attraction or electrostatic force. That's the reason that an ionic bond is stronger than covalent bond, because you have two different ions, two different charges are held together. So that makes the reason that ionic bond is pretty much stronger than covalent bonds. Quantitatively, this bond of attraction can be measured by something called a lattice energy. Lattice energy, it's an enthalpy change that occurs when a solid ionic compound is transformed into gaseous ions. So lattice energy is an indirect measurement to measure the attraction of the bond. That means that enthalpy basically means that it's heat. Heat is involved. Enthalpy is a Greek terminology for the substitution of the word heat or energy. Now, energy is needed to break up a solid ionic compound. Like, for example, if you have NaCl, which is a solid ionic compound, to change sodium chloride into completely transforming into gases, a sodium ion and a chloride ion as a gas, right? So you need to have some kind of energy, input of energy. So, how much energy is needed to break up the sodium chloride is also indirectly, it's a measurement of electrostatic force. That's how we define lattice energy, the amount of energy that you put. By the way, if you put an energy inside to break up, it's called endothermic energy. How much energy that you're going to put to break up the compound, and when you break it up, you'll be, it's 100% completion will be a solid substance has to be changed into a gas. So that is also a measurement. It's a measurement for the strength, the electrostatic force. So that's what lattice energy is about. It's an enthalpy change that occurs when a solid ionic compound is transformed into a gaseous ion. So basically, let me go back here. Um, The bond energy is enthalpy change that occurs when a given bond gaseous molecule is broken. That's what we're going to discuss about here, the terminologies first. Bond energy and bond distance. The bond distance, the optimal internuclear distance between two bonded atoms. So the distance between a sodium ion and chlorine ion. Okay, that's what we call it, a bond distance right here, which is represented as R. That's the optimal internuclear distance between two bonded atoms. So basically, the lattice energy or the bond energy, how we can able to measure the energy quantitatively. That's what we're going to discuss here. We go to here, for example, the lattice energy, like I say here, the lattice energy approximately equal to the change in enthalpy. Enthalpy, here the word enthalpy, which is means heat. Enthalpy refers to heat or energy that's applied. The change in energy or enthalpy, which is required to separate the ions to infinity. So the lattice energy basically refers as uh, U. So it has a certain constant Q. Q1 and Q2 represents the charge of the ions. In terms of, I would like to stick with sodium chloride. We have a sodium plus and a chloride minus one. So Q1 represents for sodium, Q2 represents for chlorine in this case, for example. And then the R refers to the distance between sodium and chlorine atoms meet. So the lattice energy is approximately equal to the change in enthalpy, which is delta H. Okay, delta H, that's what enthalpy is about, to separate the ions. The value of the constant K depends on the specific arrangement of the ions in the solid lattice and their valence electron configuration. So the K value for different substances will be given as a proportionally constant values. So remember that the lattice energy has certain factors. The important thing, what you need to know about lattice energy, what are the factors for lattice energies? The factors for lattice energies, when that lattice energy will be the highest one. If the numerator part, if this part is higher, then obviously the lattice energy will be higher. So the charges of the ions are higher, so the lattice energy would be higher. If the distance between the two would be higher, would be longer, the longer the distance would be, the lattice energy would be the lower. So this is a point here, what they would like to explain us. The lattice energy are highest for substances with small, highly charged ions. So you have two factors that lattice energy will be higher due to the fact that if you have charges are higher, then the lattice energy would be higher. Or if the optimal distance between the two atoms or the two ions are smaller, then basically it means that the lattice energy is also higher. So the factors are, the higher the distance would be the lower the lattice energy, the higher the charges would be proportional to the lattice energy at the same time. So, like for example, I can, without even calculating the substances, you can say that you can also predict two. If I give you two ionic compounds, let's say for example, if I give you sodium chloride versus magnesium chloride. Okay, so atoms are basically smaller. All atoms are smaller. If you know from Chem 101 or from our previous understanding that the size of the atoms are measured in angstroms. I don't know if you remember angstroms. Angstroms are like one angstroms, I believe, would be 10 to the power of minus 10 meter. You can imagine how atoms are smaller. So basically, the size of the atoms are smaller. But what makes a big role here is the charge of the ion, the Q value. Q refers to charge of the ions. So, like for example, without knowing about the K value, we can make a prediction of the lattice energy. We can make a prediction of a lattice energy between sodium chloride and magnesium chloride. Now, the lattice energy, magnesium chloride, let's say we have, let's say U2, if this is U1, which one do you think would have a higher lattice energy, magnesium chloride or sodium chloride? Just by noticing about the charge of the ion. I think that's Roger, I believe, right?
Yeah,
Roger, right? Okay,
yes, yes. Can
Roger.
you hear me?
Yes, Roger, go ahead, please.
Mm, Magnesium chloride, U2 will be higher than U1.
I agree, Roger, because just by looking up how did Roger came up to that point? Just by looking up the charge of magnesium. Magnesium has a charge of +2, versus sodium has a charge of +1. You see, so even though the atoms, the difference of the size of the atom is not that much big. So if the charge of the ion is greater, then the lattice energy would be greater. So by looking up the charge, you can also predict the lattice energy would be higher. The higher the lattice energy that you have, we'll also have a lot of factors here. Now, this will help us to understand more about the boiling point of substance. Again, this is going to lead us, for example, if we have magnesium chloride, we have sodium chloride. So we can also make another prediction here, that another chemical intuition. Which one will have a higher boiling point? Magnesium chloride or sodium chloride? In this case, what do you think? Since the lattice energy of magnesium chloride is greater, you need to have more energy to break up the bond, right? A boiling point means that you're going to change the solid magnesium chloride to gases, right? So you need to invest a maximum amount of energy to break up the bond. So that means that magnesium chloride require, or magnesium chloride would have a higher boiling point uh, than sodium chloride in order to dissociate, in order to break up the ions completely to magnesium ion and chloride ion because of the charge of magnesium. So that's how lattice energy is actually corresponding with the enthalpy. Okay, enthalpy and lattice energy, it's a matter of word, but in conceptually they are the same. Enthalpy is how much heat is needed to break up the bond. Okay, lattice energy is also, it's the same as enthalpy, but lattice energy explain as quantitatively the amount of energy needed, how much energy is needed. So they work together basically in this term. Roger, please go ahead, sir.
Yes, excuse me, Professor Fakir. Mm, uh, this sign, the sign minus in front of lattice energy. So I have a hard time to understand how the lattice energy will always be positive. Could you?
Yes. Yeah, see, here is the thing. It's a very good point that you mentioned. The K value has to be positive. However, a negative times negative will always be positive. Remember that chlorine has a charge of -1, for example, right? But we're not taking -1 in this case. We're taking the absolute value of -1. So to adjust that, we're going to put a minus sign here. Otherwise, you're going to have a negative value. Energy cannot be negative unless it's exothermic. You see, so to adjust that value, you put a negative sign on in front of K to fractionate with the negative value of the ions, the negatively charged ions, like chlorine, for instance. Do you get me? Does that make sense?
Thank you, Professor Fakir.
Okay, you're welcome. You're welcome, sir. Okay, I'm sorry. Let me go back here. Let me see if I can able to claim this. Okay. Um, yes, see, this is what I'm talking about here. The relationship between lattice energies and physical properties. Why do we need to know the lattice energies basically? Melting points or boiling points vary with lattice energy for ionic substances that have similar structures. The higher the lattice energy is, what is the prediction? Is going to have the higher the melting point. The hardness is directly related to how tightly the ions are held together. So it's also a reflection by the lattice energy. So some substances are hard, some substances are soft. It's also the way how the charges are calculated, the way how the distance between the two ions makes the substance hard or soft. The melting point or the boiling point is not by accident or by chance, but it's also directly a reflection of lattice energy. Besides, lattice energy affects the solubility of ionic substances in water. So, the higher the lattice energy, the less soluble in a compound. A compound is in water. We just commonly, like in 101, said that like dissolves like. Organic substances require organic solid, require organic solvent. Yes, it is true. But sometimes we need to ask that why do some substances can easily be soluble in water? Why do some substances would take more time to be soluble in water? You see, sometimes some substances require even hot water versus cold water. Some substances would even their inorganic substances will be quickly soluble in cold water. Again, it's a matter of lattice energy. If you have the higher the lattice energy, solubility is going to be lower and lower. So enthalpy and lattice energy are a reflection of solubility, hardness, the melting point, and the boiling point of substances. Um, it also describes the process this in which an ionic solid is conceptually formed from its component elements in a stepwise manner. Um, it can be used to predict which ionic compounds are likely to form. This is related with the lattice energy. We also bring the lattice energy with Hess laws, which helps us to calculate the lattice energy from the measured enthalpy formation for the ionic compounds, along with other thermochemical data. We may look some examples. I'll look some examples for you to discuss about how do we relate Hess law, integrate Hess law with the lattice energy. Okay, now, okay, let's see about the Lewis electron configuration, the Lewis electron configuration dot symbols. Now, I don't think we discussed about Lewis structure. Let me give you some ideas of uh, what we're going to do in chapter 8, chapter 9, basically. In chapter 8 and in chapter 9, just knowing about bonding would not be enough to understand the concept of chemical compounds. Mostly in nowadays, chemical compounds will not be just defined. What type of bond do they have? They are more defined by the geometry of the molecule. In fact, researchers, latest researchers and studies, they have shown that the effectiveness of a chemical compound is not about the concentration, how much atoms or how much chemical that you have in a compound, but the effectiveness of a compound, especially when you're studying about pharmaceutical and other medical terms, the effectiveness of substances, the effectiveness of a compound is about the way how they are oriented, the way how geometrically they are connected.
Yes.
So the shape of the molecule, not the bond, not the concentration, the shape and the orientation of the molecule would play or is playing a great role in determining the effectiveness. I'm not saying I'm not ignoring that concentration doesn't have any role, but the big the big factor for the effectiveness is the geometry of the molecule. So basically, chapter 8 and chapter 9 is focusing on the geometry of the molecule. So to understand the geometry of the molecule, we need to understand how the electrons are distributed. Especially when I say electrons, I'm not talking about the entire electrons. I'm talking about the valence electrons. The valence electrons. Yeah. What's a valence electron? Can anyone tell me what's valence electron? Can anyone tell me what's a valence electron? Do you see what I'm writing? Roger, please go ahead, please.
Yeah, I think valence electron are electrons which are on the, the outermost shell.
Yes, sir,
Yeah.
I agree. The electrons is the outermost shell of an atom. We are focusing on the valence electrons. They are the one who really form a bond. They are the one who plays a role in forming a bond of the atom. So to understand the geometry of the molecule, we need to understand how electrons are distributed, how the valence electrons are distributed. So here it says one of the configurations that to understand the geometry of the molecule, we begin with Lewis electron dot system. The Lewis electron dot system is a system that can be used to predict the number of bonds formed by most elements in their compounds. So, what are the basic rules to write an element of Lewis dot symbol? Here are the four dots here. Place dots representing its valence electron one at a time around the element's chemical symbol. Up to four dots are placed above, below, to the left, and to the right of the symbol. Ensure elements with four or fewer valence electrons have no more than one dot in each position. Next dots for elements with more than four valence electrons are again distributed one at a time, each paired with one of the first four. So, for example, here is an example for a loose dots symbols for fluorine. It's a whole structure here, but what we can able to understand that um, from our Chem 101, we discussed that fluorine is just for example, is found in group 7. It's an element found in group 7. If you notice, group 7 elements are called the halogen groups or halogen family, right? Hey, the halogen are group 7. Now, please, this is my advice for you. Every time, please have a predictable in front of you so that things make easier. Not only the PowerPoint, have a predictable next to you so that the flowing would be you can able to follow that how they are related to each other. The reason why I'm saying that fluorine is in group 7, why is fluorine is in group 7? If it is in group 7, technically fluorine has 7 electrons. So if you count the dots here, the dots represent the number of electrons. So we have 2, 4, 6, 7 electrons here. You see, first we have to fill the pair of electrons as you see here, 2, each orbital holds 2 electrons, and the remaining electron, which is this guy right here, which is one, which is unpaired electron. That's the one really makes how to say a bachelor. That's a single one. That's the one who really is interesting to create a bond with the other element. Okay, so that when we put electrons in this symbol, it's called electron dot symbol. It's electron dot symbol. Okay, so electron dot symbol um, basically is a reflection of Lewis structure. So we have to start from a single element. Like for example, if I have nitro, oh, hold on, what happened here? If I have let me write this here. If I have, for example, nitrogen, right? I have an element of nitrogen. So I'd like to draw the Lewis electron dot symbol for nitrogen. What do you think would be the electron dot symbol for nitrogen would be? If you have a predictable, you can give me a prediction. The electron dot symbol for nitrogen. Anyone would like to try the electron dot symbol for nitrogen? Nitrogen, if you have a periodic table, nitrogen is in group 5. Okay, if it is in group 5, basically nitrogen has 5 electrons. So the electron dot symbol for nitrogen would be 2, 4, and 5. This is the electron dot symbol. Victoria, I see your hands, Victoria.
Yes, I wanted to do the one for nitrogen, but you already.
Okay, Victoria. No, Victoria, having stayed there, Victoria, how about oxygen? What do you think would be the electron dot symbol for oxygen, just for a practice
Ox-
for the
Oxygen has 6
six? Yes. How do we know oxygen has six?
because
Mhm.
the it's in the it's in group
Periodic table.
6.
It's in a group
Yeah,
six.
on the periodic
Exactly.
table.
Exactly. The group number always is a reflection of how many electrons does an atom has. So the loose structure for oxygen is going to be six. By the way, it's six. It's because of that six. It's in group six. So the valence electron for oxygen is six. So oxygen has six. So basically, that tells you the number of groups, the number of it tells you the number of valence electron. It tells you the group, and we put six dots here to represent the Lewis structure. So the Lewis structure, I would say, is a foundation for drawing the geometry of the molecule. Understanding the Lewis structure would help us to build up the geometry of the molecule when we're dealing with chapter 9, or chapter 8, to understand the more complex nature of the geometry of the molecule. The basic point is understanding the Lewis structure. So the Lewis structure again starts with the knowing with the valence electrons. So using these dot symbols to describe covalent bonding, we also keep continue this. Arrange the atoms to show specific connections. We need to know how do we arrange the atoms to show specific connections. There's an important point. Determine the total number of valence electrons. You see, determines the total number of valence electrons in the molecule or the ion. You're not going to do the valence. By the way, you're not going to do the Lewis structure um, just for molecules. You do for ions as well. Ions like sulfate ion or phosphate ions. Okay, we have to do the valence, the Lewis structure for them as well. Place a bonding pair of electrons between each pair of adjacent atoms to give a single bond. It means that if we have a pair of electrons will be represented as a single bond. If you have two pair of electrons, that is a reflection of a double bond. If you have three pairs of electrons, that is a reflection of a triple bond. So you may have single bond, you may have a double bond, you may have a triple bond. Now, single, double, or triple again is also a function of how many electrons are participating in terms of connections, to show the geometry of the molecules. Beginning with the terminal atoms, add enough electrons to each atom to give each atom an octet. Okay, the word octet, so far the word octet is used here, but octet, the idea of octet is that having eight, having eight, having eight, okay, having eight basically means that every atoms in a molecule will be satisfied, will be participated, or will be stable, would be stable. So that's how octet means. But we're not. This is what was discussed in chemistry 101. That our goal is why do atoms lose or why do atoms gain electrons? One of the reasons is that to be stable. What is the word stable means? The word stable means to achieve octet. If an element has an octet, then it's satisfied, it's stable. But we will also practice certain expectations not only atoms will not be stable just by having octets. There are molecules or there are ions that are they are stable when we do the Lewis structure. They are stable, but do not necessarily have octets. Okay, we're going to discuss that in this chapter as well. Uh, we'll see. We'll practice some examples. I may give you some examples. If any electrons are left over, place them on the central atom. Um, I would like, for example, let's continue on this and then maybe we can do some practice here. Lewis electron structures explain stereochemistry. Here it says the number of bonds formed by an element in a neutral compound is equal to the number of unpaired electrons it must share to complete the octet. Okay. Maybe I don't know how um, the way how your periodic table is arranged. This slide is used uh, um, the numbers like 17, 16, 15, 14. So the reason why some slides they use these numbers because they count transition elements as well. You know, periodic table has two sections: main group of elements, and then you will also have transition elements. If you count the main groups of elements along with transition elements, you can come up with 17. But 17 means that it's group 7, okay? And then for the elements in group 16, 16 means in group 6. Group 15 is in group 5. Group 14 is in group 4. If you just, that makes things easier to me. I believe that makes things easier for you as well. We can count elements, we can count elements in a way that if you count the main groups of elements. So for the elements in group 7, who are the group 7 elements? If you have a predictable, I suggest you like for every class, if you have a predictable, it might be easier. Group 7 elements are like, who are they? Like chlorine, I believe bromine, iodine, fluorine, right? Etc. Etc. These are group 7. So for the elements of group 7, the number of bond is going to be 1. You see, for example, you have hydrogen and fluorine over here. What it means that, let me continue. For the elements of group 16, which is 6, group 6, give me one example of group 6, for example. Oxygen, right? Oxygen is in group 6. Or sulfur is also in group 6, right? So oxygen, how many electrons oxygen needs to achieve octet? To be 8. How many electrons oxygen need to achieve octet? Octet means that to be stable, how many electrons oxygen need? Basically, oxygen needs how many electrons?
So,
2. Excellent. 2 electrons, right? 2 electrons. So relate the number of electrons that is formed, the number of electrons that's needed to achieve octet, and the number of bonds that's formed, they are identical. They are the same. You see, that's the reason that oxygen forms 2 bonds here. I'm writing in red here. See, oxygen forms 2 bonds here. Because oxygen is a group 6, it requires 2 electrons. So number of electrons to achieve octet, maybe I can write here for you. Let me write in a new slide here as a rule that it makes things easier for us. Let me just say that, oh, hold on. In Lewis structure, the number of electrons needed to achieve octet, and the number of bonds to form loose structure is the same, or identical. Okay, this is a paraphrase of the previous slide actually. For instance, for example, oxygen is in group 6. So how many oxygen is in group 6 needs 2 electrons to achieve octet, and hence it forms 2 bonds. So a good example is oxygen will form 2 bonds with hydrogen. Maybe I can write in here. Okay, oxygen forms 2 bonds. It's not by chance, it's not by accident, because oxygen requires 2 electrons to achieve octet. At the same time, it forms 2 bonds. This might be a good example. Okay, I mean, for example, you can also talk about the bond between hydrogen and chlorine. It's going to be H. I mean, let me just change the hydrogen with chlorine. If you look on chlorine, it's only 1 bond. You see, it's only 1 bond because chlorine is in group 7. So it requires only 1 bond. You see, this also can be extended to other elements like nitrogen. Nitrogen forms a bond with hydrogen. If you have NH3, for example, if nitrogen is central atoms, it requires 3 bonds here. Why nitrogen requires 3 bonds? Again, go back and look for the periodic table. If you look on the periodic table, let me just make everything.
It's found in group 5.
Yes, it's in group 5. So nitrogen requires 3 more electrons to achieve octet. So it requires three more bonds. You see, the number of bonds an element or an atom needs to achieve octet, and the number of bonds are identical or similar here. So this is a good explanation for the slide that we had earlier here. Let me just take this note here. I was talking about this one here. For the elements of group 7, I don't like 17, but I will say 7. The number is 1. For the elements in group 16, that means 6. This means like 6. This is like 7, so that we are avoiding confusion here. Group 15 refers to group 5. So they require 3 bonds. For group 4, they require 4 electrons. So you can look on the pictures here. For example, we have carbon here. Carbon is in group 4, so carbon has 4 bonds here. Nitrogen is group 5, so nitrogen has 3 bonds here. And it goes on. Oxygen has 2 bonds and fluorine has 1 bond. Depending on which group they are located, how many electrons do they need to achieve octet? And it's basically reflecting with the bond, reflects with the number of electrons, the number of valence electrons to achieve octet. Yes, Roger, please go ahead. Is that the previous hand, or did you raise your hand, Roger? Let me go back. Okay, there's another person. Brett, I think Brett.
I raised my hand first.
Okay, I didn't hear you. Okay, go
Yeah.
ahead. Okay, Roger.
I was I said that when you say when we are talking about the bonds, you refer to the single bonds because you have three types of bonds here.
Yeah, yes, yes,
Either single, double, and triple bonds.
yes, yes.
But in Lewis structure, only single bonds you are talking about, right?
Yes, yes.
Okay, okay, I got you.
At this point, yes. At this point, yes.
Okay, okay.
We're going to extend on that. But I'm going to come back to the double bond. When do I apply double bond? When do I apply triple bond? I'm going to go back. I'm going to explain that later on, Roger. Brett, Brett, Brett. You raise your hand, Brett. Is that?
Yes, Professor. Can you hear me?
Yes, yes. I hear you now, Brett. Go ahead.
All right. So is it correct to assume that in group 3, it would be 5 bonds, like boron? Or is that wrong?
Not, not. This is a great question, but I have to tell you that no. Now, okay, bonds are formed. The Lewis structure.
I meant electrons. Is it?
Electrons, yes, yes, but
Yeah.
technically with this explanation, I can say yes, but theoretically, I mean practically, which elements are forming bonds? It's non-metals, not metals. Now, group three, by the explanations that I made, you're right. Nothing is wrong with that. They are group three. They require 5 electrons. They should have 5 bonds. Yes, sir. I agree with you. But practically, metals do not share electrons. See, bonds,
Okay.
yes,
Right.
bonding actually comes by sharing electrons. Then now question arises here. Question comes. The question comes, which elements are sharing electrons? Metals or non-metals? Now we have a problem. Non-metals are the one who are sharing. So bonding starts from group four, not from group three. Because
Okay.
yeah, yeah.
All
Because
right. Thank you.
you're welcome, Braid. So that's how it is. So we have to now, when we share electrons, it's only non-metals are the one who are sharing electrons. Formal charges. The way how formal charges can be explained that formal charge, to calculate formal charge, non-bonding electrons are assigned to the atom on which they are located, and bonding electrons are divided equally between the bonded atoms. An atom or molecule or ion has a formal charge of 0 if it has the number of bonds that's typical for that species. Let's see if I have example here. One thing I hate about um, this PowerPoint doesn't provide you examples. So I would make my own examples next time. Okay, now what is formal charge first of all? You see, the reason why the reason why we need formal charge, you may have different Lewis structure for the same molecules. You may have different Lewis structure for the same molecule. So you need to know which of the Lewis structure is consistent. You see, which of the Lewis structure is consistent. So, a formal charge to me is an accountant. Is a way like IQ, like a quality control. I have Braid here, I have Roger here, I have Victoria here. I'll ask them, I'll give them like a molecule, for example, I'll say BF3, bromine trifluoride, and draw a Lewis structure for bromine trifluoride. These three, they will bring me 3 different structures. Okay, so one way or the other way, unfortunately, not 3 of them may be right. Uh, so we have to find out. We have to find out. We have to set a parameter here to identify which of the 3 Lewis structure will be the right structure. So that's why we need formal charges. Formal charge basically can be used to distinguish among Lewis structures. Loose structure with a state of formal charge closest to zero is usually the most stable. It's just jumping to go one form to the other, but let me see if we can do one example. Um, I didn't bring an example today, but I'll bring you examples next Thursday so that we can able understand better of the. Let's see if I have here. Okay. Okay. So. Okay. Okay. So we okay. How do we calculate the formal charge? Okay, let's. This is a good point here. The way how we calculate formal charge, the difference between the number of valence electrons in a free atoms and the number of electrons assigned to it in a particular loose electron structure is defined as a formal charge. So formal charge is the result of the difference of the valence electron for the free atom minus the non-bonding electrons, which is assigned to that atoms, plus the bonding electrons divided by 2 in the loose structure. That will determine the formal charge. Now, the criteria of a formal charge is that the lowest the number, the lowest the formal charge that you have in the loose structure, it means that it's more stable. Okay, so let me, the lowest the formal charge closest to zero you have, it indicates that it's more stable. That's one criteria. The next criteria is that if there is a negatively charged ion, the negative formal charge is located in the highest electronegative element. The highest electronegative element. Please, okay, write this down. These are the two criteria that we need to take into consideration. The lowest the formal charge is closest to zero indicates that it's more stable. That's one criteria. The next criteria is that whenever we have a negative formal charge, that negative formal charge has to be located in the highest electronegative element or atom. I would like to use not element, but the best way is atom. I think let's just remove this word here. I would like to say atom or ion. Okay, these are the two criteria, and then that way would be the best litmus test to determine the formal charge. Okay, so let me see if I can able to create some examples here. Okay, let me start with the smallest example. Okay, let's first draw the loose structure to understand more about how we can. Hold on. See. Okay, let's first draw the loose structure. Okay, let's start with the loose structure for. Oh, my, make it bigger. Okay, draw the loose structure of ammonia or NH3. Okay. So there were dots. I mean, you can go back to the previous slides and we can able to discuss about that. But we can start from the point of view that the first thing that we need to know is that determine the total number of valence electrons. Okay, of the atoms presented. So in this case, we have nitrogen. Nitrogen has 5 valence electrons. We also have hydrogen. How many hydrogen we have? We have 3 atoms of hydrogen. So that's going to be 3 electrons. So altogether, we have 8 electrons. This is number 1. You follow me? That's number 1. You need to determine, the second step is you need to determine the central atom. The central atom, which one is going to be on the center? Okay, it's not like just by guess. We have to identify there are certain criteria to determine the central atom for the loose structure. Okay, one of the criteria that we can apply here is that one of the criteria that we can apply here is that mostly the larger the atom, is considered the central atom. Okay. The other criteria is the one okay, yeah, the one that has less electronegative. Okay, if the first one doesn't satisfy, the one that has less electronegative is considered as a central atom. You have 2 options. Okay, so in this case, I would take, based on this criteria, I would take nitrogen as a central atom because nitrogen is larger than hydrogen. If you look on again, how do I know that? Nitrogen is on the right of hydrogen. So as we go from left to right, it's going to be higher, larger and larger. They have more outermost shell electrons. So they are getting bigger and bigger. So nitrogen is larger than hydrogen. So it's going to be the, let me go back again here. Okay, so nitrogen will be on the center. So here is the idea. If it is larger, the idea is that it can have more room to accommodate electrons. Okay, it can have more rooms to accommodate electrons. So if you want to change that idea and you want to put hydrogen in the center and nitrogen on the side, hydrogen doesn't have enough room to accommodate the number of electrons because remember, we have here 8 electrons, 8 valence electrons, where Lewis structure, the way how Lewis structure is doing that, how we are able to distribute the electrons, the 8 electrons, around the nitrogen and hydrogen in a proper way. In a proper way to determine the geometry of ammonia. So you don't have any choice. You have to put nitrogen because nitrogen can occupy more space than hydrogen in its orbital. So we put nitrogen and we put hydrogen on the side. You see? Now, we have to have a bond to each of the bond between each bond costs you about a pair of electrons, 2 electrons, right? So we need to have a single bond. We start with a single bond. Okay, that was the reason that I think Roger asked me, you're talking about the single bond. Yes, we start with a single bond first. Then if there is excess electron, then we go to the double bond. We're going to go to triple bond, by the way. Now, remember that now we used up actually 2, 4, 6 electrons. So how many electrons are left? 2 electrons are left. All right. So now 2 electrons are left. So we're going to put that's going to be step number 3. The remaining electrons. The remaining electrons would be the remaining electrons would be on the central atom. The remaining electrons would be on the central atom. So in this case, on the central atoms. So in this case, I'm going to put the remaining 2 electrons on the nitrogen. And that way, every element is achieving octets. Like nitrogen have 2, 4, 6, and the remaining 2 electrons here 8. So we disposed all the 8 electrons. We disposed all the 8 electrons. So we can able to determine that way that we have that way we distributed. This is the right structure for Lewis structure for ammonia actually. So the Lewis structure for ammonia. I would definitely, before we discussed about formal charges and other further futures, I wanted to make sure that all of you understanding how to make a Lewis structure for a certain molecule or ions. So, for example, so let me do a second example. So draw the Lewis structure for HCN, hydrogen cyanide, HCN. Okay. So now, what's the first step? Just like what we did for ammonia, we can do the first step. The first step,
Do you find a valence?
yes, find uh, the total valence electrons. Yes, valence electrons um, for the entire atoms. Okay, so in this case, we have hydrogen has 1 electron, carbon has 4 electron, nitrogen has 5 electrons, right? Depending on the groups where we are located, where they are located. So we're going to have 1 plus 4 is 5, 5 plus 5. We're going to have 10 electrons. You see, we're going to have 10 valence electrons. So we have to work on these 10 electrons to distribute the Lewis structure, to distribute each of the electrons, and it's not just distributing, also to accommodate them in a way that they are going to be stable. They are going to be achieving octet here. So the second choice in this case is a difficult choice, and you have to think about it. We have to determine the central atom. Okay, determines the central atom. So in this case, what do you think would be the central atom? Hydrogen, carbon, nitrogen. To be on the center. And why? Roger.
Yeah, I think carbon will be in the center.
What's your reason for that, Roger?
I don't have a reason.
Yes, ca- carbon is the center. Yes, I agree with Roger. I will give the reason. Carbon, compared to hydrogen and nitrogen, has a lowest electronegative. Carbon is lowest electronegative than nitrogen and hydrogen. You see, so that's the reason. And then nitrogen and hydrogen will be on the side. Okay, this is how you start with identifying the elements. So now you're going to start with pair them with a single bond. Okay, by putting a single bond, you're going to consume two electrons. So we already used up 4 electrons. We have 6 electrons. Okay, now the rule said that you're going to put the 6 electrons around each atom to make it to achieve octet. So I'm going to put, for example, two here, two here, two here, makes the nitrogen happy. Okay. Now we have an issue here. Nitrogen is stable because there's a pair of electron here plus lone pair. By the way, I'm going to put here as a lone pair. These electrons here are considered as lone pair. They are not shared pair. Lone pair because they are only belongs to nitrogen. Okay. Now, however, we are not fair in distributing the electrons. We are making nitrogen rich, stable, but we're not making the carbon and the hydrogen. The hydrogen is, by the way, is stable because, as you know, hydrogen requires only 2 electrons to achieve octet. Hydrogen has one valence electron, needs to have another 1 electron, so hydrogen is okay. But I'm having issue with carbon. Carbon has 2 and 2, only 4 electrons. For carbon to be octet, we have to take a pair of electrons from nitrogen. We have to take a pair of we have to borrow a pair of electrons from nitrogen. So by doing that, maybe like I'm going to take this part here. Okay, let me just by borrowing a pair of electrons, I'm creating a double bond here. Now carbon has 2, 4, 6 electrons. It's better, a little bit better, but it's not that much better. So we may have to take another pair of electrons from nitrogen. So a double bond still doesn't satisfy an octet. So we have to go to a triple bond in this case. We have to borrow another pair of electrons from nitrogen. So we may have to remove this actually. And hold on, let me write this. So we have to create a triple bond, and we have a pair of electrons here. Now, I want you to count with me about carbon and nitrogen. Carbon has this, by the way, these bonds here are belongs for both carbon and nitrogen. They share electrons. So we have 2, 4, 6 plus 2. Carbon has 8, which is good. Nitrogen also have 2 ampere electron here in this section, and then has 2, 4, 6. You see, now a triple bond basically is a good optimum, a good option for making a loose structure for hydrogen cyanide. So the correct hydrogen cyanide is going to be HC triple bond N. Now someone might say, wait a minute, I have 8 electrons. Okay, oh, the lone pair is here. Someone might say, wait a minute, I can have H minus C with N. They both have 10 electrons distributed. They both have 10 electrons distributed. But this one is right, but this one is wrong. So that's the reason that we need formal charge to identify which one is right and which one is wrong. So we don't have enough time now. I'm going to explain you more on next class. I'll bring you more example, but for today, let's take this as an example.